Hello everyone, this is Arohi and welcome to my channel. So guys, in this video I'll talk about DenseNet, dense convolutional neural networks. So DenseNet is an image classification algorithm and it was developed to improve the accuracy of a model by handling the problem of vanishing gradients. So this vanishing gradient problem is a very common problem in deep neural network, and deep neural network simply means when we have lots of hidden layers between input layers and the output layer. And due to this longer path between the input layer and the output layer, information vanishes before reaching its destination. And DenseNet overcome this vanishing gradient problem and provide us high accuracy compared to other convolutional neural networks by simply connecting every layer directly with each other. So let's see this DenseNet in detail. And guys, the topics which I'm going to cover in my today's class are what are DenseNets. After that I'll show you the architecture of DenseNet, and while showing you this architecture I'll explain you each and every small thing of that architecture. Okay, and finally we'll see the advantages of DenseNet over other image classification networks. So let's begin with the DenseNet. So guys, DenseNet have different variants. So the variant which we are discussing today is DenseNet 121. This 121 simply denotes the number of layers in a network. Okay, so you can see that input will go to a convolutional neural network where we are using a filter size of 7 by 7 and we are using a stride of 2. Then we have a pooling layer and the filter size we are using over here is 3 by 3 and stride is 2. And then guys, in DenseNets we have dense blocks. You can see we have 4 dense blocks, these green blocks, 1, 2, 3 and 4. So we have 4 dense blocks, and inside every dense block we have convolutional layer, different number of convolutional layer. You can see that in dense block 1 we have 6 convolutional layers. Okay, con 1 into 1 and con with a filter size of 3 by 3. So we have 6 such layers. And in dense block 2 you can see that we have 12 convolutional layer. In dense block 3 we have 24 convolutional layers, and in dense block 4 we have 16 convolutional layers. So in DenseNet 121 we have 4 dense blocks. Okay, and after every dense block there is a transition layer. You can see transition layer. So I'll explain you the working of dense block and a transition layer in some time. Right now we are just understanding the overview of this architecture first. So after dense layer we have a transition layer, after second block also we have a transition layer, and after third dense block we have a transition layer. Okay, and guys, now see this picture. Below this dense block I have unfolded this code, and you can see here these are convolutional layer 1, 2, 3 and up to 6. So we have 6 convolutional layer. Each layer is connected to every other layer in a dense block. Okay, inside a dense block each layer is connected to every other layer. Okay, and okay guys, before understanding this architecture in more detail, let's understand the working of dense block in detail, and then we'll come back to this architecture. Okay, inside a dense block, so I'm just showing you, you can see here this is a dense block 1, right? We have 4 dense block and this is the first dense block and it has 6 convolutional layer. When you unfold it you can see these numbers are convolutional layers. So we have 6 convolutional layers, and inside dense block each layer is connected to other layer, and each layer receives the feature maps from the previous layer. You can see here, okay, this is a dense block, this gray feature maps x0, I have given a name x0 to it, gray feature map. These are the input features we are providing to the dense block. Okay, when these input features we provided to first convolutional layer generated few features. Okay, and we are also we are concatenating these old features with the new features, and you can see the feature maps like this. Okay, and each layer receives the feature map from the previous layer. Now you can see This is a convolutional layer 2. These green feature maps are generated by the convolutional layer 2, but this layer will also receive the feature maps from the previous layer, this purple and the gray features. Okay, so we are concatenating this green features which we get from this convolutional layer 2, and we are concatenating it with the other two feature maps which we have collected from the previous stages. So in the same way, you can see each layer receive feature map from the previous layer, means the input of a layer inside this dense block, the input of a layer is the concatenation of feature maps from the previous layer. So this will be the input to this layer, right? This will be the input to this layer, and we are concatenating these features with the feature map of that particular layer. Okay, this is how it works. And so what we can say that each layer is adding up some features on the top of the existing feature maps. So on these existing feature map, second layer added these feature. On these three different feature maps, third convolutional layer added these red features, and fourth convolutional layer added these yellow features on the top of these feature maps, right? So after the sixth convolutional layer, you can see that we have the concatenated feature maps from all the convolutional layers, right? So this is the working of dense block. Now guys, one thing which is very important to understand over here is that you can only concatenate the feature maps if the size of those feature maps are similar. Okay, so means if you want to concatenate these features with these gray feature, you can only concatenate them if the size of those feature maps are same. Okay, so and guys, see what we are doing is we are working on convolutional neural network. DenseNet is a convolutional neural network, right? And in convolutional neural network, the important part of that convolutional neural network is that we downsample the input image. Okay, so just take this example, VGG16 example. Here you can see that we are giving our input image of size 224 into 224 into 3, and after processing this image, and you can see after downsampling the last convolutional layer giving us that image, we have downsampled the image which is of size 224 into 224 into 3. We have downsampled it to 7 into 7 into 512. Right, so what we have done is we have downsampled the image, and every convolutional neural network downsampled the image, downsampled the input image which we provide to the network, right? But what I am right now, what we are discussing is we want to concatenate the feature maps. And how we can concatenate the feature map? We can only concatenate the feature map if the size of those feature maps are similar. But guys, if you are performing downsampling on the image, downsampling will change the size of feature map, right? Getting my point? Means if we will perform that downsampling, which is the important part of convolutional neural network, then the size of feature map will change. But for concatenation, the rule is we need the feature map, all the feature maps should be of same shape, then only you can concatenate them. Now, how to handle this problem? We want to perform both the operations. We want to perform downsampling also, because it is a important part of convolutional neural network, and DenseNet is a convolutional neural network. So downsampling, we will perform downsampling. And the second thing which we want to perform is we want to concatenate the features. Now let's see how we can perform both these things simultaneously. So let's go back to the architecture again here. So guys, inside a dense block 1, 2 and 3 and 4, inside the dense block where we are concatenating the feature maps, there we will not perform downsampling. Okay, because why we will not perform downsampling in dense blocks? Because inside a dense blocks we are concatenating the feature maps, right? So, and this transition layer will perform the downsampling. So what I'm saying is we will not downsample the feature maps inside the dense block, but we will downsample the feature maps when those feature map will reach to transition layer. Let me explain you in more detail. So dense block 1 will give you some feature maps, right? Those feature maps will go to the transition layer, right? Now transition layer is having this conv 1 into 1 layer, and then we have a average pool layer of size 2 by 2 with stride 2. Over here we will downsample the feature maps which we receive from here. See, the output of previous layer will become the input to the next layer, means the feature maps generated, the concatenated feature maps from the dense block 1 will become the input to the next layer, transition layer. Transition layer will perform downsampling on them. After performing downsampling, those features will go to dense block 2, and in dense block 2 also, this is the dense block 2. Here we have 12 convolutional layers, right? So 12 convolutional layer means here we have 6 layers. This is for block 1, right? In the same way you will have 12 layers now, and every layer, again the same concept will follow over here also. Each layer receives the feature from the previous layer, right? And we are performing the concatenation on the feature maps. All right, this is what we are doing. Every layer will add up some feature on the top of the previous concatenated feature maps. Okay, so this is how every dense block will work. Then when you'll work over here, after concatenating the feature maps of all 12 convolutional layers, and here again inside this dense block we are not changing the size of feature maps because we are concatenating the feature maps over here. Once you concatenated the features of all 12 convolutional layers of this dense block, those feature maps will go to the transition layer. Here again we are performing the downsampling, and guys, this convolutional layer 1 into 1, this will perform the downsampling, and these two things will perform the downsampling. Again dense block 3, here we are having a 24 convolutional layer. That means feature maps, concatenated feature maps of 24 convolutional layers will be the input to the transition layer. Transition layer will downsample them, and again we have a dense block 4. In dense block 4 we have 16 convolutional layer. That means you will get 16 feature maps from here, and this way finally you will get some feature maps from here. And after that we have a global average pool layer, and the filter size over here is 7 into 7. And then finally we have a fully connected layer, and we are using a softmax activation function, and this will provide you a output. Suppose you have given an input image of horse, so your algorithm will classify it as horse by processing this whole data. Okay, and guys, when we say convolutional layers over here, in every dense block we have convolutional layers, right, with a filter size of 3 by 3. This convolutional layer consists of batch normalization, then ReLU. After that we will use convolutional layer of size 3 by 3, and then we use this dropout. So whenever we are writing this convolutional 3 by 3, it simply means first we'll do batch normalization, and then we'll apply ReLU activation function. Then we have a convolutional layer of size 3 by 3, and then we have a dropout. Okay, and inside this transition layer, what all things we are actually using in transition layer? So we'll do the batch normalization first, and then we are using a ReLU activation function. Then we are using this convolutional layer 1 by 1, and after that we are using dropout, and then finally we are using this average pool layer of filter size of 2 by 2 with stride 2. This is exactly the sequence how the things are happening in this transition layer. Okay, so guys, this is the architecture of DenseNet 121. Now the next thing is, let me tell you what is there next. Now let's see the advantages of DenseNet. So guys, in simple convolutional neural network, in standard convolutional neural network, what happens? We have input, we give input to the first convolutional layer, right? In normal convolutional network, what happen is we pass the input to the first layer of the network, then the output of that layer becomes the input to the next layer, and this is how it will work for all the layers. And finally classify on the basis of the features maps which it received from the final layer. The final layer feature map in deep convolutional neural network, what happen is the feature maps from the very last layers are the high level feature, are the complex features, right? So our classifier will classify the input image on the basis of the feature maps which we get from the final layers of our network. Means on the basis of the high level features which we get from the last layers of our network, our classifier will classify the output on the basis of that. But in DenseNet, what happens in DenseNet? Every layer is connected to every other layer. Okay, so classifier in DenseNet, classifier uses features of all complexity, right? Means it takes the feature from the early layers of the network where the resolution of feature are high, but that those features are not very informative, and it also takes the feature from the middle of the network, and it takes a feature from the last layers also where the features are very complex. Means it is this DenseNet is considering all kind of features. It is considering the simple features, the means it will collect the feature maps from all the layers, and then on the basis of that it will give you a classification on the input image, right? And next thing is in DenseNet, in the beginning of our today's class only I've told you that DenseNet solved the problem of vanishing gradient. How it solved the problem of vanishing gradient? Just see this picture. First, input is going to the final layer and our algorithm will calculate the error and gives us the output, right? And every layer is connected to every other layer, right? This is our forward pass. And in backward pass also, after calculating the error, after calculating the loss function, that loss function is sending the gradient information to every layer, even to the early layers of the network, right? So in DenseNet, each layer has a direct access to the gradients from the loss function. That means information flow is in this network is very good. Error signal can be easily sent to the earlier layers of the network, and this way the early layers can can take the advantage of that gradients, get that information, and this is how they solve the problem of vanishing gradients, right? By connecting the each layer with every other layer of the network. Now the next thing is, guys, if you have read this DenseNet paper, so they have mentioned few advantages like strengthened feature propagation, or you will hear encourage feature reuse and reduce number of parameters. Now what these things are? Strengthen feature propagation. Okay, let's take an example. Suppose the feature learned by the layer 1 are directly accessible by layer 5 or layer 4 or layer 6, right? So strengthen feature propagation simply means one layer already learned something, then layer 4 or layer 5 or any further layer can use that information. Okay, and feature reuse simply means this is again the similar kind of thing. So there let's suppose layer 4 doesn't have to learn about about the features which already layer 1 have learned, because it can access the information directly by concatenation, right? So that means layer 4 doesn't have to learn a feature learned by layer 1, because that information can be used by layer 4, because we are using the concatenation over here. Every layer is connected with every other layer, right? So these are the benefits of it. And guys, there is one more thing. If you will study this DenseNet, you will hear the concept of this growth rate. Now what is this growth rate? See, growth rate simply means how much information we want to add to the network by each layer. Okay, so let me explain you with example. Suppose the k is equal to 3. K means growth rate is equal to 3. This 3 simply means every convolutional layer can add 3 feature maps to the existing feature maps. Okay, so let's see with this example. So these are some gray features. Okay, and this is a dense block 1. Dense block 1, guys, all these layers are connected with each other. Sorry, I hadn't done that connection over here, but all these 6 layers are connected with each layer, because inside dense block each and every layer is connected. Okay, so conv layer, these are the features of conv layer. And if you set k is equal to 3, that means convolutional layer 1 can only produce 3 layers. Okay, and convolutional layer 2 is also producing 3 layers. So the 3 feature map from the first convolutional layer, and we are adding the 3 feature maps from the second convolutional layer. So now we have 6 feature maps. Now convolutional layer 3 will add 3 feature map. So 6 feature map from here, and we are adding 3 feature map by convolutional layer 3. So now we have 9 feature map. Now convolutional layer 4 will add 3 feature maps in these 9 feature maps, right? So what is happening is every convolutional layer is only adding 3 feature maps in the existing feature maps. Okay, and by the end of this dense block 1, we have written into 6. That means we are having 6 convolutional layer, and all the 6 layers are adding 3 features. And by the end of this dense block, that means if the value of k is 3, if growth rate is 3, then by the end of this dense block 1, where we have 6 convolutional layers, we will have 18 feature maps. Now these 18 feature maps will be the input to the transition layer. So guys, this is how it works. So I have given you the basic explanation of this DenseNet. Now in my next video, I'll show you the practical implementation of DenseNet. So that's it guys. I hope you like my video. Thank you for watching.